Thank you for the interest in solid phase microextraction. I have been working for the last 30 years developing SPME technologies and methods to facilitate different application of the solid phase microextraction, as you can see in the pictures demonstrating those applications. So you can see that you can use SPME for automated high throughput analysis in gas chromatography, liquid chromatography, on-site sampling and analysis, remote sampling with the drone, in vivo sampling in animals, and eventually even human trials we recently published. So in my talk, I will emphasize the fundamentals of solid phase microextraction and address some of the mysteries. So the mysteries are how can you use such a simple technique in so many different applications in so successful way? I will try to explain you that. And also Miseries, but the scientists who try to use principles of exhaustive extraction in solid phase microextraction. I will start with some short historical background, then talk about the fundamentals of SPME as simple as possible, then unique features of the SPME compared to exhaustive techniques and resulting differences and limitations, and how to design good devices including coatings and different supports for the coatings, different formats of SPME facilitating above mentioned applications. So I am a scientist which focuses on fundamentals in sample preparation. I want to convert sample preparation as to be a scientific tool which works based on fundamentals which are well understood. By doing so, in my research group, I found that you can design very interesting projects with the technology, developing a range of different applications, but in addition to it, we can optimize sample preparation technologies, not only SPME, in such a way to get more information about the investigative system. I will mention that in a few places in my talk. The other area which I want to emphasize is that in my research, I emphasize the ability to integrate. So SPME is a perfect integration tool which can integrate sample preparation into the chromatography, for example, or even directly mass spectrometry, or microscopic tools, or even electrochemical measurements. So it's a very unique tool from that point of view. We can integrate sampling in addition to sample preparations for introduction. So it's of great interest to chromatography, but also to mass spectrometry as well. SPME is a green technology because it uses only small volume of extraction phase, but it also has a good functionality, which means it meets detection limits required by the given method, as well as the cost efficiency and the operational principle and simplicity, facilitating on-site sampling, which is another big area of sustainable oncochemistry. I will give you examples of those type of developments in my lab. One of it was to facilitate efficient way of water analysis, and the other one looking at the complex samples by looking at determining drugs in meat samples. Now, at this point, I want to mention that green approach to oncochemistry is not only important that we eliminate organic solvents, which of course is not a big deal considering the relatively small amount of solvents used compared to chemical industry, but where it's important is to facilitate by those new technologies more analysis. So facilitate analysis which allows us to monitor the environment, food, or as you know, recently it was very important to monitor the viruses in the COVID to be able to monitor spread of the disease. With the same, from that point of view, it's also important to design the efficient tools for chemistry based on green chemistry principle and functionality. The SPME origin is based on my initial work by doing laser desorption, introduction to gas chromatography. In that approach, I use the polymeric oligomers, which are deposited on the tip of the fiber, and use a laser desorption fertilization to introduce it in the front of the column. And as you see on the right, in upper chromatogram, we were able to get very nice chromatogram with all peaks separated. On the other hand, if you just use the solvent injection with those oligomers dissolved in it, you have a broad peaks because of the poor volatilization in the injector. In this research, I noticed that it's not only possible to introduce the polymers, but I also was able to see some solvents associated with the process. So after some thinking outside the box and thinking about the different devices, I was able to introduce this paradigm shift of extractions and introduce this concept of SPME device based on microsyringe, where I replaced the wire, which is used as a piston in microsyringe, by the coated fiber. And by moving the coated fiber in and out of the needle, like a plunger, I was able to protect the coating during the septa penetration. So this led license of the technology to Superco, which then developed a commercial version of this device. As you can see here, you can purchase it in anytime, anywhere in the world. And then, of course, fully automation of this process by the autosampler as it is a syringe, so it can be fully automated. So instead of injecting the solvent into the injector, now you can do extraction using a thermostatic agitator. So it can do extraction at constant temperature, and then you place it, extracted components in the fiber in the injector to localize it. So of course at the beginning, there was a lot of concern by the scientists. Anytime you have a new technology, currency technology, there's a lot of questions, and they had a difficulty to get any funding for the project, primarily because they said, how can we get the high sensitivity, because the low small amount of extraction phase. Later on came up these questions regarding saturation and swelling effect due to the high volume of the sample compared with the small volume of the extraction phase of the fiber. So to address those issues, of course, there was a high enrichment I will talk about in a moment regarding the LEDs. And in terms of swelling and saturation effect, we have approaches, many different approaches. I'll talk more about it later, but it basically reduced the phase ratio, design better selectivity of the extraction phase, but extraction times, and use the direct extraction versus headspace to use the limitations of the of hydrophobic components, and then remove the interferences, something what we are looking at right now. The other question which was quite often raised also was looking at, can we analyze real sample considering its complexity? And of course, solution was to use the headspace SPME and matrix compatible coatings. I mentioned that in my talk. There's also concern about the slow extraction kinetics because surface to volume ratio of most of the configuration of SPME are low. And this could be addressed by using thinner coatings and high surface areas and devices, as well as magnetic particles. Also, the coil fiber and vacuum SPME has been introduced to increase the kinetics. The issues related to how to get quantitative data. It's actually very easy, but not much different to of extraction, how to optimize SPME, which has always been more challenging. It has been addressed very well in the textbook of solid phase microextraction, which is available from every year and from my website, as well as what we teach in SPME course. Unfortunately, I don't have enough time to go into details, but I'm sure they will be quite clear to you after this lecture. So I will talk about fundamentals. which to some of you looks like a black magic, as is shown in here. But in fact, I will try to make it very simple. In some modeling we use, we usually quite sophisticated modeling, like console modeling. But here, I will just explain to you using one simple formula describing distribution constant. So as you can see, distribution constant is the ratio of activities of animals in the extraction phase compared to the coating, which corresponds closely to the ratio of concentrations, which is because of the low concentration of the animals. Now, in exhaustive extraction, of course, the objective is to have not enough volume of the extraction phase to facilitate complete transfer of analyte to the solvent, which has a higher affinity for its analyte compared to the sample matrix. In SPME, we reduce the volume of the extraction phase down to microliter, or even I showed you one example in SPME PESI to nanoliter. So in fact, we are forming equilibria. We are not doing exhaustive extraction. So in SPME, we very often talk about the key value, but in exhaustive extraction, we don't even mention that. We just say we want to have the conditions for exhaustive extraction. So this is the big difference. Now, don't confuse the microextraction in the fundamental format that I was mentioning, keeping the volume of the sample high and the volume of the extraction phase low, with the microextraction based on neutralization, so basically reducing the extraction phase and the sample volume at the same time. So this could be still exhaustive. And in fact, you can use a single fiber exhaustive extracted from the small volume of the sample. So just to explain to you better what I mean and what the advantages of microextraction versus exhaustive extraction is shown on the example of analyzing the water sample. So as you can see the table here, you have different parameters. The water volume is the same. The volume of the solvent typically is 40 milliliters, while in microextraction is 1 microliter. The key value is the same. The concentration is the same. The recovery, as you can see, in exhaustive extraction 100%, while in SPME it's only 0.1%. But you can see the amount injected is identical. Why? It's because of the enrichment factor. If you look at the formula of the enrichment factor above, you will see that it talks about the ratio of amount of analyte extracted versus the volume of the extraction phase. This is the concentration of the extraction phase, divided by initial concentration of the sample. So it's basically in SPME very close to the distribution constant. So in this case, we chose toluene, which has a distribution constant of 1,000 for both solvent and TDMS. While in liquid extraction, the initial enrichment due to the partition into the solvent is only 25 because you actually diluted the sample by facilitating exhaustive extraction. So you diluted the analyte in a sample matrix. So in order to enrich the sample further into the evaporation, but in SPME, since you have a high concentration in a coating, you can inject it directly into GC column, and you can obtain basically this identical sensitivity. So you can see the fundamental difference why you are basically using the same principle. You're changing the volume of the extraction phase. And one of the important features I want to emphasize this point is that because you don't change the concentration of the sample, you can actually sample directly from the source, like river water or air, and put it directly into the instrument. So you basically integrate sampling and sample preparation in the process, facilitated on-site analysis. Now you can even take it further. Now, if you have a microprobe, as it is in PESI, you have a 1 nanoliter of the extraction phase, so you only coat the tip of the probe. You put it in a sample, then you rinse it, removing the residue of analyte or of the interferences, usually bound, and then introduce it to the PESI system. You'll get the range of the desorptions, because the way it works per se, as is shown in here. So you basically dissolve the analytes, which are dissolved by the solvent picked up from the bottom, and then you spray it. And so, and the amount of solvent picked up that is only picoliters. So you have a system where, for example, you can have a volume of the sample of about a few microliters, nanoliter of the extraction phase. So you have this enrichment, as is shown here, associated with the K extraction phase sample distribution constant. And you also have a small volume of the desorption solvent where you not exhaustively dissolve, and you have another K associated with the desorption solvent extraction phase distribution constant. So you have a product of two Ks giving you extremely high enrichment. Of course, the signal is very short because very few picoliters of solvent, as you can see. As you are progressing, you can repeat this desorption from the same probe many times, as is shown in the bottom. Now, the definition of solid phase microextraction has been already given. This is basically the idea is that we use the extraction phase, which is in solid form. It could be even physicochemical liquid like a PDMS, attached to some type of support, which we place it in the sample. And I want to emphasize that a lot of devices we use routinely work based on non-exhaustive extractions, like flow injection analysis, electrospray or electrochemistry, for example, and many others. So it doesn't, the definition doesn't specify what the format of this phase is, but it's typically a coating. So what I mentioned before, it could be a fiber, it could be tube, called a tube vessel, magnetic particles, and depending how many magnetic particles you use, you can use the exhaustive mode or microextraction mode, some discs to increase the surface to volume ratio, or stirrers for convenience. So this has been recently quite nicely summarized in the Anchor Chemistry Review and orally in this YouTube presentation below, where you can see this idea of the microsyringe in the center, then on already available commercial devices, and then presently what we work on, it means directly coupling to mass spectrometry, underwater sampling, drone sampling, medical applications, and single cell analysis. Those things are still under development. So, of course, you can use the SPME in different ways, direct extraction for clean samples, headspace for complex samples, and you can also use another approach for complex samples using a membrane protection. And this membrane protection you can implement different way. So basically, you can have a separate membrane, which is not as efficient, but you can build that membrane as a part of the coating, as I will mention later. Independently what type of format it is, or whatever extraction you do, the best you can do will be extraction controlled by the boundary layer. You don't want to have extraction controlled by the thickness of the coating. So the coatings in SPME, good SPME devices are thin to facilitate fastest extraction. As you can see, the boundary layer is symmetric and static when there's no flow, but there is a flow, unidirectional flow. You have actually inhomogeneity of the boundary layer. Yeah, so you need to remember that in order to do that, to eliminate this effect that behind this device you have a thicker boundary layer, you need to change the flow. So the best actually extraction approach, agitation for extraction approach in SPME is vortex agitation. You can also use very rapid flow. And this is, as you can see here in the number 3, where you have a turbulent flow rather than laminar flow. So by doing that, you can eventually go to the optimization, and the best way to do extraction at equilibrium. And equilibrium, as I mentioned before, the amount of analytes extracted is related to the concentrations and the parameters of the fiber. It means distribution constants between the fiber coating and the sample metrics for given analyte, as well as the volume of the coating. In that case, when you reach equilibrium, you are not dependent on the convection conditions or time. Its results are more precise, as I'll show you in a moment. You can also slow down, speed up the analysis by using this linear range at the beginning up to about 30% of the equilibrium value. You have close to linear dependence, where the amount of analytes extracted is proportional to surface area, diffusion in the central matrix, and inversely proportional to the boundary layer. However, here you need to be extremely careful about reproducible agitation and timing. So Y, as you can see here, is if you are close to equilibrium, the change in the amount of extraction, depending on time or agitation, is very low. While when you are at the beginning of extraction, it is quite high, resulting in high RSDs. Now, let's focus in a headspace extraction. So you can see here what type of equilibrium occurs in complex matrices. Yeah, so you have a binding matrix. It could be proteins, because it could be a biological mass, and you have an analyte absorbed on it, and they partition into freeform. This freeform partition to headspace. Now, of course, headspace is a very effective way to remove the contact between this matrix, but not for the analytes which exist in the free form. It's available to headspace. So if you have a situation where the target analytes are available in headspace, but also interferences which are at high concentrations, you really did not fully eliminate the matrix. So you can have a situation if you leave fiber long enough that you collect enough analytes, which can cause swelling and saturation. So let me talk a little bit about that. So the process of swelling is associated with absorption. It's very rare, basically because you need to introduce a lot of analytes onto the coating that its proportion is such large in the coating that it creates the changes in the physical chemical properties. So in its physical chemical properties. So it changes in coating physical chemical property. In absorption on the hand, as you can see on the right, you have absorptions in the large pore or small pores. You are limited by the absorption of the surface. So usually they are much stronger absorption property than absorption polymers, but the analytes does not diffuse in the body of the sorbent. It's just surface is available because of the very low diffusion coefficient in the matrix of the sorbent. So in this case, it's much easier to cause absorption and saturation by absorption. As you can see on the right, you have a linear range where there's enough space for absorption available, and then eventually when you're getting close to 100% coverage, you have this problem of nonlinearity, which is called saturation. And absorption, you have very long linear relationship, and eventually you can also see some swelling, which, as I mentioned, change the physical chemical property. You also have a deviation from linearity. So how to eliminate this? So as I mentioned to you before in one of the beginning slides, is that way to do it would be to reduce the volume of the sample or increase the volume of the extraction phase. In that case, you have enough capacity to deal with the interferences. The other way would be to use a coating less affinity towards interferences. For example, polar coating, when you target analytes or polar analytes, while the interferences are more hydrophobic analytes, or using coating with specific property towards the analytes, using short extraction time. I'll show you that in a moment. And PDMS, rather than solid coatings, as it is less prone to the saturation. And direct extraction versus headspace is also a good trick, because usually those compounds which cause interference, they are hydrophobic and they have poor solubility in water. So if you use direct extraction, the rate of extraction is substantially reduced due to limited solubility in water. We also noticed this overcoated fibers, which are matrix compatible with SPME devices. They also eliminate to a large extent saturation. They're available from Supelco. And then modification of the matrix dilution or removal interference is something which we are working on it right now. So when you want to use the show the extraction time, why does it work? Well, you can see if you have an extraction of heavier hydrocarbons and lower hydrocarbons, depending, of course, on the solidity and affinity of the coating, the lower affinity amyloids like naphthalene, it really degrades much faster, within 2 minutes. And you wait longer, you accumulate the heavy amyloids, which can introduce so much amyloid that can cause the displacement. So there is no reasons to go beyond 2 minutes if your target amyloid is naphthalene. I will change the gears now. I talked a little bit about the thermal disruption in the injector. One thing what I want to emphasize is that carrier gas linear flow is very critical in SPME because, as you notice, for semi-volatile components, the key value in the injector at elevated temperature, like 250, for example, on backing is 13, so it's not close to 0. It's quite a substantial number. So the extraction occurs as it is in gas chromatography. So it's a gas chromatography stripping process. The faster gas flow, yes, fast dilution. Yeah? So it is in here. Faster gas flow, faster removal from the fiber into the front of the column. In order to accomplish that, what we need to do is to use the narrow flow liners. You know, they are commercially available from different manufacturers, because in SPME we don't use the solvent, so we don't need to have about 1 millimeter liner to accommodate expansion of the droplet when it goes from liquid phase to gas phase, which takes about 1 milliliter, so 1 microliter volume. Why in SPME you just only volatilize the amyloids, the coating, the extraction phase. In this case, which takes the role of the solvent, is non-volatile. So it's also important to make sure that you depress the plunger rapidly, because otherwise, if you leave it for a long time, the fiber and the needle, there could be a bleeding of the amyloids from the needle, causing double injection. So, but as long as you do it within a second or two, it's fine. And of course, autocentric usually do it automatically. Now, when you do all those conditions, what I mentioned to you is that the liners has the low volume, so you cannot very conveniently introduce a calibrant. So we introduced the concept of in-vial standard gas generation, and it's available, for example, PS Technologies. It's also available from our group and from our website if you're interested. So what we do here is we have a sorbent device, which is like a thin film micro extraction I mentioned later, which is spiked with the amyloids into large amount, and we pick up the compounds reproducibly by exposing the fiber in the headspace at fixed temperature for fixed time. And so you can do reproducible injections, as you can see many of them. So you can calibrate it. So in our group, we use it for QC of the GC and the validation of the methods. Now, I would like to show you the comparison between the SPME and exhaustive extraction. So this is a very interesting comparison, as you will see. As I mentioned to you before, I already tried to give you that in a more fundamental way, but I will now show you the experimental results. So you can do micro extraction technique on the same size as the SPME, solid phase micro extraction. So you can micro solid phase solid phase extraction device and build a trap out of this. Yeah, so you have here you have a trap, and you can see you can even have advantage because you have no sorbent, but this is exhaustive extraction, which I show on the right. And then SPME, the very far left, have a much lower amount of solvent extraction phase. So why would you like to use SPME? You have a needle trap, which we developed too. So here's the example, how does it work? Needle trap, so you have the PEC needle, you can do sampling via the some type of syringe, but more precisely we use a metering pump, and you can fill the needle, take it to the lab, and facilitate desorption. As you can see, this is a special cycle here to facilitate very efficient desorption by the carrier gas. So those devices are also available commercially from PS Technologies, Schindler, and Elmer. So I will show you the difference and why would you consider SPME in such a situation. So we created a complex sample, which is a smoke, so it contains particles, and we use it to extract it with a needle trap and SPME at the same time. Here I want to emphasize in the SPME, the amount of analytes extracted is related to the distribution constant, volume of the extraction phase, and concentration. And of course, assuming that the volume of the sample is large, as it was in this case, and in needle trap, it is just a volume concentration as long as you don't have breakthrough. And the other difference is that in SPME, the extraction occurs via the boundary layer, so you actually are not able to extract the particle, which has a low diffusion coefficient. By the needle trap, you pick up everything. Now you see the differences. Now, in both cases, you use the same sorbent, and you optimize breakthrough volume for benzene and the amount and the equilibrium time for alethrin, which is the active component in mosquito coil smoke. And you can see that you, of course, extract much more benzene in needle trap because you have more sorbent, close to breakthrough, but not all the components. So in SPME, you progressively extract more components as the K value increases, and then you see some drop due to the fact that the affinity of the particles becomes larger. So the free concentration is very low, and eventually you see alethrin. So the question is, why would you like to use one sample versus one method versus the other? Well, in SPME, as you can see, you measure the actually free concentration, you equivalent the free concentration, and in needle trap you measure total concentration. So if you want to measure the amount of compounds which are affected mosquito, which affect mosquitoes, will be a free concentration. But if you want to measure the environmental impact, you want to use needle trap because eventually the particles of the smoke fall on the ground and reach to the environment, causing the problems. Yeah, so basically this is the reasons why SPME is very useful, is because it gives you the free concentration, which you can also calibrate the total concentration in fluids and tissue, not as easy in the gas samples. So in the gas samples, you want to use both needle trap and SPME if you want to have both numbers. Now you can see that there is this very nice area where sensitivity of SPME is very large, and this is the area of fragrances. Here's where the vapor pressure is high and the key values affinity towards the coatings are high, so we can pick up a lot of the analytes. So this is the reasons why SPME is so popular in fragrance analysis. Now, if you want to increase the sensitivity of SPME, you need to increase the volume of the extraction phase. And in order to do it, to not increase the extraction time, you need to have very thin coatings. So we use a thin film micro extraction, so you can see you have pieces of carbon mesh, which is impregnated with a sorbent, and the extraction phase volume is close to 100 times larger compared to single fiber. And you can desorb it, of course, not directly in the injector, but using the, for example, line exchange system, which is provided by Kerstal, or by taking element for portable instrumentation. Now you can see that the sensitivity, if you compare the upper traces, that the sensitivity is about 50 times larger, as would be expected by the larger capacity of the film, volume of the film keeping the same thickness. So equilibration time is the same. If you compare, on the other hand, with the twister, which is based on increasing the thickness of the coating to increase the capacity of the fiber, that causes, of course, the increasing the extraction time. So this is the advantage of using thin films. Now, we also developed this thin film application for water analysis, and of course you can do it directly on site, but we use it in combination with bottle sampling. So because the standard way of doing the samples, instead of taking the analytes in the bottle and putting in the small vial and put it on the outer sampler, where we're losing some hydrophobic analytes on the surface of the bottle, we actually place the thin film directly in the bottle. And so the extraction occurs soon after sampling. And if you do that, you can see that in fourth column, the thin film microextraction bottle sample has much, much lower detection limits. One or two orders of magnitude lower compared to standard liquid extraction method performed by Maxim Analytics, the company we worked with, the first row. Now I'll tell you a little bit now about complex analysis by doing direct extraction. So in this case, we just want to extract it directly from the matrix. And the reason why I want to do that here is an example of extraction by direct extraction on the right, head-based extraction of apple homogenate. You can see we have a much more larger molecular weight species, means higher boiling temperature compounds, as well as more polar compounds extracted. And this is accomplished by using the protection layer. So you have a support, could be a fiber, a mesh, extraction phase, and then the protection layer, which has the possibility of dealing with the complexity of the matrix. So you can see use a PDMS, PEN, polychloroneutral, or Teflon. They have a protection layer. So we have been using those things. And the way it works is you can see that the sorbent pink in pink color, in yellow you have protection layer, put in contact with the sample, so the matrix doesn't contact the sorbent directly, just through the protection layer, performs the extraction, removal of the matrix, and rinsing typically, and then desorption. Now, what we found that this process is very, very efficient, because it not only provides clean extraction, but also balanced coverage, because the balance is provided by the matrix interaction with the analyte. So hydrophobic analytes has a lower free concentration compared to the hydrophilic analytes, yes? And in addition, we have this boundary layer which protects the compounds, large matrix component reaching the fiber, in addition to, of course, this being biocompatible. So if they are just absorbed quickly on the surface, you can rinse it as water. So here it doesn't work. So for polar compound like a morphine, you can see there's no much difference in extraction efficiency in PDMS and plasma, but in hydrophobic compounds like steroid here mentioned on the left, the difference in plasma extraction and PBS is very, very substantial. So, and this is due to this matrix, which is shown in here. So there's interaction, competition between the fiber and the matrix, and this produces this balanced coverage. So relatively, all the analytes extract to the same extent, independent of the polarity, up to the polarity limit determined by the property of the solvent. And this has been proven by many publications. So they are listed here as essential publications where we can extract different analytes with different property, which and therefore it's a tool useful for metabolomics. And also in a clean way. That means because we extracted in the other free concentration, we eliminate dissolving large amounts of interferences such as phospholipids and reducing them to the LC column. So you can see at the bottom you have a trace associated with the liquid extractions. So this is the blank after 40 runs of liquid extraction. And then on the top you have a blank on the column after 40 SPME runs, even multiplied by 100 times, and you don't see this phospholipid band. So of course that's creates a situation where you don't have a matrix effect. So variations you extract from the clean matrix or from the real matrix, the results are within plus minus 20% of the real value. But there is also another thing I want to mention, that in lipids analysis, we actually see all the lipids, because all the lipids have some free concentrations, some of them associated with the critical micro concentration, for example. And since we don't have a matrix effect, we see all the lipids, not only those which are not interfered, not only those which are not interfered by the phospholipid band. One thing what I want to emphasize, that in SPME, it is important to prepare the samples correctly, especially for hydrophobic analytes. As you can see it here, and the publication below emphasizes it, is that it's very difficult to prepare the free concentration of the analyte in the unsupported matrix with usually clean solvent, because analytes are not stable. They go to the glass, they absorb on the glass. And you can see it as progressively, if you go from the left to right, you have a higher log P, this becomes a bigger problem. So basically, as is shown in here, is the analytes mostly, if you have very hydrophobic analytes like that, they are stick to the matrix. So if you have it in the matrix, you don't have a problem. It's just creating the standard clean solutions. So here's the example of explaining how it works in a tissue, like a muscle tissue, heart tissue, brain tissue, which I'll talk about in a moment. So this was an example of the lung tissue. So we compared the static extraction of the PBS. We created the agar gel of the PBS, agitated PBS, and then you have a matrix direct extraction of tissue. As you can see, static extraction is very slow. The agitated extraction much faster, but SPME on the tissue is even faster. It's only 20 minutes versus when you have agitated, it takes about an hour. And the reasons why, because you are not limited by the mass transport in the boundary layer, since the tissue exists in the boundary layer. The analytes are provided from the sorption site with the boundary layer, considering that the amount of analytes extracted is much lower compared to the analytes that exist in the spike PBS. So applications. So we use this in looking at the tissue sampling in an automated way. You can see you can have a 96 fiber type of system. And the reason why you use a 96, because the extraction time is slow, as I mentioned to you at the beginning. So it takes about 90 minutes to go with the whole process. So it's not highly compatible with SPME. But if you use a hunger sample at the same time, then it's becoming close to 1 minute per sample, which is much more compatible. You go through preconditioning, extraction, wash, and desorption, and look how wonderful the results are. So you have you can see the matrix effect is very, very low. And if you compare to liquid extraction technique and catchers technique, which is micro liquid extraction, you can see that the matrix effects are much more manageable, much smaller compared to those techniques, and the results from accuracy and precision point of view the same way. So looking at the complex matrix like the tissue and veterinary drugs, we did over 100 veterinary drugs, we see huge advantage of SPME methods. So because of the clean extraction, we also try to do direct spraying to mass spectrometer by using blade with a particular format. With a tip format. And basically, we prepare such a device. We can do it in, of course, parallel way, but we use a metal blade so we need to deactivate it by the pen, and then put on the tip the sorbent. Then we can immerse it appropriately in the sample, in 96 volt plate typically, and then spray it, and get the very good performance even in such a system. We have a little bit more matrix effect, plus minus 60%, but it's still quite amazing because you dissolve all the compounds, including interference, with a mass spectrometer. And then you have a good precision in the terms of accuracy and precision. And so it's amazing. Now, this device is available from Restec. Now, as I mentioned to you before, the long-term goal in SPME would be to perform it directly on site and carry it into the labs for many devices analyzed at the same time. So you can do on-site sampling and send it to the device, to the lab for analysis, as is shown here. Now, last point I want to mention is this in vivo sampling. So in this case, the beauty of SPME is that it eliminates need for quenching, since you equilibrate the SPME coating directly with the living system. So what is extracted is a true representation of what's in the living tissue. In addition, not having the matrix effect, it produces very powerful tool for in vivo monitoring. You can monitor actually the changes, the difference of SPME versus other techniques. And this has been published in this paper. And you can see what changes occurs during the regular biopsy. So this is basically chemical biopsy tool, what SPME is. It allows to just extract chemistry, do not extract the tissue. And here is just to demonstrate the power of this technique. So if you compare, for example, in brain analysis compared to microdialysis, shown on the right, you can see that the results for neurotransmitters are the same. But what's more interesting is that where the strength of SPME is in the lipid area, the more lipophilic compound. And the microdialysis has more advantages in more soluble compounds, while SPME more hydrophobic compounds. So if you want to have a full good representations of the chemistry in a brain, for example, you can use both techniques. Now, we also used recently SPME to facilitate on-site sampling in the hospital. So this is an example of sampling the lungs for doxorubicin, which is anti-cancer drug. You can see the hairs of the fiber, some small fibers sticking from the tissue. And you don't need to use a mass spectrometer if you have a targeted analysis. So you can develop, for example, for doxorubicin, we have developed fluorescence detector. So you can see the fiber on your left, and you have an excitation beam from the laser, and then emitted light monitored by the photo multiplier tube. So anyway, this brings me to the end of my presentation. I strongly recommend you to look through the textbook, Handbook on SPME, possibly attend the courses, SPME courses given. I emphasize all the topics here, but one thing at the end I want to again emphasize that more effort needs to be done directed towards characterization of matrices, interaction between analytes and matrix components, because this will not only help the development of a successful SPME method, but generally any type of sample preparation methods. This is group before COVID, last picture. COVID now I have a little bit smaller group, but the most important for you is to look at my website. There are a lot of interesting information there. And finally, I want to encourage you to attend the XTech 2021, which is going to be in Alicante, Spain. I think it's going to be likely remote, but they also have made the decision is not do it at least partially on site. I'm looking to answer any questions.